Hello everyone, I'm Charlie Claremont, Technical Director at Synaltic, a data consulting company founded in 2004 and specialized in modern data architectures. For over 10 years, I've been helping organizations with their data transformations, and today I'll talk about something that concerns us all, how Apache Iceberg enables proactive technical debt management. Raise your hand if you've ever migrated a critical data infrastructure in production. Pause to observe. Keep your hand up if that migration took longer than expected. Laughter. And now, who's been blocked by architectural choices made 5 or 10 years ago? Choices that seemed smart at the time but today prevent you from evolving? That's exactly what we call technical debt. And in the data world, this debt accumulates particularly fast because our architectures couple too many layers together. Today, I'll show you how Apache Iceberg solves this fundamental problem, with concrete production examples. Netflix migrating over 1 exabyte, Adobe managing 1 petabyte with only seconds of downtime, and many others. Let's take Hadoop as a classic example. For years, it was the standard for big data. The problem, point to diagram, everything is coupled. HDFS for storage, Yarn for orchestration, MapReduce for compute, Hive Metastore for metadata, and Hive for queries. At first, it works. It's even pretty good. But after a few years, you want to migrate to the cloud? Impossible without redoing everything. You want a faster query engine than Hive? Very complicated. You want to scale? You have to buy a whole new cluster. This monolithic architecture creates massive technical debt, and that's exactly what companies like NetApp experienced. NetApp ActiveIQ is a platform that analyzes over 10 trillion data points per month to monitor enterprise storage equipment worldwide. Their Hadoop infrastructure? 33 mini-clusters with over 4,000 cores. 7 petabytes of data. A decade of history. Point to problems. Look at the symptoms of technical debt. 45 minutes on average for a query. Imagine waiting 45 minutes for a simple dashboard. Storage and compute are coupled. You want more compute capacity? You have to buy more disks too. You want more storage? You also pay for unused compute. Configuration is so complex it requires Hadoop experts, and they're expensive and hard to recruit. Point to cost, but the worst part is this statistic. Teams spend 60% of their time searching and preparing data, and only 40% doing analysis. That's technical debt. We paid to build a system that, 10 years later, prevents us from working efficiently. And redoing everything from scratch? Unthinkable at petabyte scale. That's where deconstruction comes in. Julien Ledem, who created Apache Parquet and is a member of the Iceberg Project Management Committee, formalized this principle of deconstruction. Read quote with emphasis. A monolithic system is functional until the day you need to evolve. The solution? Point to objectives. Split into independent layers. Each layer has a clear responsibility. We can change storage without touching compute. We can change the query engine without touching data. Apache Iceberg is the concrete implementation of this vision. Let's see how. Here's the Apache Iceberg architecture. 5 clearly separated layers. Point to each layer going down. Layer 1, the catalog. It's your table registry. Where they are, what their schema is. You can use Hive Metastore, AWS Glue, Nessie with Git-like versioning, Snowflake's Polaris, or Databricks Unity Catalog. Interchangeable. Layer 2, Iceberg Metadata. This is the format's core. Snapshots enable time travel. Manifests track all files. No need for expensive S3 listings. Statistics enable query optimization. This layer guarantees ACID and consistency. Layer 3, the compute engine. Spark, Trino, Dremio, Flink. Any of them. The same Iceberg tables are accessible by all these engines simultaneously. You choose the engine by workload. Dremio for interactive BI, Spark for batch and ML. Layer 4. File formats. Parquet for classic analytics, ORC, Avro. And tomorrow, Lance and Vortex for AI workloads, with embeddings and vector search. Layer 5. Storage. S3, Azure Data Lake, Google Cloud Storage. On-premise, HDFS, MinIO. Cloud agnostic. Point to message at bottom. The crucial point. Each layer can be migrated independently of the others. We can change catalogs without touching data. We can change query engines without redoing storage. That's proactive technical debt management. Now let's see how this works in practice with 3 real migration demonstrations. First demonstration, catalog migration. Natural intelligence. A company analyzing consumer behavior, had 400 production dashboards fed by hundreds of Iceberg tables on Hive Metastore. Their need, move to Glue Catalog on AWS. The business constraint, 0 minutes of downtime. Dashboards must continue working during migration. Let's see the code and migrate a Hive catalog to Nessie, a catalog that works like Git for your data. Branches, tags, merges, but for data tables. Let's look at the actual production tool. This is Iceberg Catalog Migrator from the Nessie project. Point to section 1. It's a Java JR you download from GitHub releases. Currently at version 0.3.2, actively maintained by the Nessie team. Point to section 2. You configure it with a simple YAML file. Define your source. Here, Hive Metastore with Thrift connection. Define your target, Nessie with REST API. And critically, point to warehouse lines. Notice both use the same warehouse location on S3. That's the zero copy magic. No data moves. Point to section 3. The migration command is straightforward. You specify the config, the mode. I'll explain that in a second. The namespace and table. The delete source false flag is crucial for safety. It keeps the Hive table so you can roll back if needed. Let me explain the modes. Pause for emphasis. Register mode. Just registers the table in Nessie without deleting from Hive. Perfect for testing. You verify everything works before committing. Migrate mode. Full migration. It creates in Nessie and optionally deletes from Hive. Point to section 4. For production migrations, you typically do bulk operations. The all tables flag migrates an entire namespace, hundreds or thousands of tables, in one command. Point to features. The tool includes everything you need for production. Dry run mode. See what will happen before doing it. Batch processing handles large table counts. Failure tracking. If something fails, it tracks state, and you can resume. Multi-catalog support. Works with Hive, AWS Glue, JDBC catalogs, Hadoop, REST, Nessie, even custom catalogs. Now let's move to storage migration. Second demonstration, storage migration. DB Cargo is the freight division of Deutsche Bahn, German freight trains. They manage 2,600 locomotives and 80,500 cars, with massive amounts of sensor, maintenance, and logistics data. Their infrastructure? 4 completely saturated on-premise data warehouses. A simple SQL join took several minutes. They were forced to delete historical data due to lack of space. And expansion costs? Prohibitive. Point to objective. Migrate to AWS S3. Unlimited storage, elasticity, predictable costs. But how do you move terabytes of critical production data without breaking everything? The answer: progressive migration with real-time synchronization. Here's the migration architecture. Point to section 1. First step: synchronize data with MC, the MinIO client that also works with S3. We configure both locations, the old on-premise and the new S3. Then, critical command. Point to watch, McMirror, watch. The watch flag activates continuous real-time synchronization. Every new file on the old system is automatically copied to S3. It runs in the background during the entire migration. Point to section 2. Now, the Iceberg genius move. While synchronization is running, we use a transaction to change the table's write.data.path property. Look at what happens. Point to stars. Old data, still on-premise, still accessible. Iceberg knows where it is, thanks to manifests. New writes? Go directly to S3. Queries? Continue working without interruption. They read from both locations, transparently. It's progressive migration. No big bang. No weekend of downtime. The system stays in production during the entire migration. Once all old data is synchronized to S3-, and we can verify this by counting files, we can shut down the old system. Point to results. DB Cargo migrated successfully. 0 downtime. Today, unlimited storage on S3, predictable costs. And most importantly, their teams spend 60% less time searching for data and 60% more doing analysis. The system has been running in production since 2020 without issues. At Synultic, we've replicated this approach for Azure to AWS migration. Third and final demo, query engine migration. Shopify, you probably know it, one of the world's largest e-commerce platforms. Petabytes of transactional data. Thousands of tables. Their legacy infrastructure? Hive with data in gzipped JSON. For large analytical queries, we're talking 1-hour execution time. The planning phase alone consumed thousands of terabytes of memory. Point to objective. They migrated to Trino for interactive queries while keeping their data on Iceberg. Iceberg's promise: any engine can read the same tables. But there's a challenge. SQL dialects are different. A Hive query doesn't work directly in Trino. How do you handle this? The solution: SQL-Glot, a Python SQL transpilation framework created at Netflix. Point to Redshift SQL. Here's a typical Redshift query. DATEADD, getDate, decode, proprietary Redshift functions. Point to transpilation, one line of code with SQL-Glot. We say, read in Redshift dialect, write in Presto dialect, because Dremio and Trino use Presto-compatible SQL. Point to result, and there you go. SQL-Glot automatically converted DATEADD, day -30, getDate, to current_date, interval 30 feet day. Transformed decode into case when, kept what's compatible as is. The accuracy? About 70% for complex queries. The remaining 30% require manual adjustments, typically custom UDFs or very specific cases. But 70% is huge. It significantly accelerates migration. Point to Shopify results. The results at Shopify are spectacular. 96% reduction in planning time. 96% reduction in memory used. We go from thousands of terabytes to less than 100. 95% reduction in execution time. 1 hour becomes 3 minutes. On the slowest queries, 99.9% improvement. Point to multi-engine, but the most interesting thing is the architecture they set up. They don't use just one engine now. Trino for interactive BI and dashboards. Spark for batch jobs and ML pipelines. Flink for real-time streaming. And all these engines read and write to the same Iceberg tables. No duplication. No synchronization. Iceberg guarantees consistency. That's true compute portability. Netflix does the same with Spark, Trino, and Presto. Airbnb uses Spark, Trino, and Hive on the same data. At Synaltic, we have clients doing Dremio for BI and Spark for ML, same Iceberg data lake. Now let's look at the future. Let's talk about the future. The Iceberg v4 specification is under development, with production release expected for 2026-2027. And it goes even further in proactive technical debt management. Point to encrypted tables. First point, encrypted tables. Today, if you need to encrypt your data for GDPR or regulatory compliance, it means rewriting all your files. At petabyte scale, that's weeks of processing and enormous costs. With v4, encryption becomes a table property. Instant activation, zero copy. Take Adobe with their petabyte. They could activate encryption in minutes instead of weeks. Point to variant type. Second point, the variant type. For semi-structured data, JSON, with constantly evolving structures. Today, either you use a string type and lose optimizations, or you define a rigid schema and have to change it constantly. The variant type combines MongoDB's flexibility, no rigid schema, with Iceberg's ACID guarantees. No more continual schema migrations. Point to expression transforms. Third point, expression transforms. Imagine, you partitioned your data by day 3 years ago. Now with volume, you want to switch to monthly partitioning for optimization. Today, full rewrite of all data. v4, online reorganization, without rewriting. Netflix, with their exabyte, could reorganize partitions without stopping the system. Point to vector type. Fourth point, the vector type. With the explosion of AI and machine learning, everyone is manipulating embeddings. Those 768, 1024, 1536 dimension vectors representing text, images, audio. Today we store them as binary arrays. It's a workaround. With v4, embeddings become first-class citizens. Native type. And coupled with Lance and Vortex formats via the file format API, Iceberg becomes the unified platform for classic analytics and AI. Point to row-level operations. Fifth point, row-level operations v2. This is critical for compliance. GDPR, right to be forgotten, personal data correction. Today, a delete on Iceberg means a scan and partial rewrite. On large tables, it takes days. v4 promises operations 100 times faster. GDPR goes from technical nightmare to manageable operation, even at petabyte scale. Point to specialized formats. And finally, next-generation formats. Lance, developed by LanceDB in partnership with Microsoft Research. Presented at Iceberg Summit 2025. Performance, 2,000 times faster than Parquet for random access. Essential for AI, model training, feature stores, vector search. Vortex, from Spiral and Microsoft Gray Systems Lab. 30% speedup on TPCH analytics benchmarks. Optimized for mixed workloads, analytics and AI combined. Point to timeline, realistic timeline, production in 2026-2027. The file format API is in community review. Lance and Vortex implementations are in alpha. But the important message, Iceberg anticipates future needs. AI, compliance, security, everything is planned in the architecture. That's proactive technical debt management.
To conclude, proactively managing technical debt with Iceberg rests on 4 fundamental pillars. Point to Pillar 1. First pillar, architectural decoupling. The 5 layers we've seen, catalog, metadata, engine, data, storage, are truly independent. This isn't theory. Point to examples. Netflix migrated over 1 exabyte. Adobe, 1 petabyte with only seconds of downtime. Shopify, 99.9% improvement on critical queries. These migrations are real, in production, publicly documented. Point to Pillar 2. Second pillar, mature tools available now. This isn't vaporware. Point to list. The Nessie Catalog Migrator, open source, used in production. MC Mirror for real-time storage synchronization. SQL Glot for SQL transpilation with 70% plus accuracy. An active community, Iceberg Summit 2024, had 2,200 plus participants. And at Synaltic, we have the expertise and we support our clients on these migrations. We don't just sell consulting, we get our hands in the code. Point to Pillar 3. Third pillar, open standards. Iceberg is under Apache Foundation. Transparent governance, no single vendor control. Point to compatibility. Snowflake donated Polaris. Databricks supports Iceberg in Unity Catalog. Nessie, Dremio all compatible. You're never trapped. It's anti-lock-in by design. Point to Pillar 4. Fourth pillar, continuous evolution. V4 arrives in 2026-2027 with encrypted tables, vector types, row-level ops. V2. Point to anticipation. Iceberg anticipates future needs. AI, compliance, security. Everything is in the roadmap. No refactoring, incremental evolutions.